To talk you about reactionary delays in the European network. As Ingo said, Pablo gave us a talk 2 weeks ago about the same problem but in the US. Well, Pablo is finishing his PhD now, so he had to pack a lot of stuff in the same talk. I, on the other hand, I have kind of more room, so I will be able to explain a little more in detail how this kind of models works, what is the approach, and I will highlight some differences which are bigger probably than you expect between at least they are bigger than we were expecting between the European and the US system. So okay, we start with a bit of motivation, and well, that is easy. If you talk about this kind of problems, you have to talk about money. So here I have two references with cost estimates for the delays in the Europe and in the US. Now, you might notice that the figures are rather different. This is not because the European system is fantastically more efficient. It's that they are measuring different things. So, in the European one, we only have operational costs, which basically mean things like my aircraft is late, I want to arrive on time, so I have to fly faster to recover delay, but if I do that, I will have to consume more fuel, so I'm spending more money. As estimate, there are also more indirect costs, such as I have to pay dinner to the passengers because the aircraft is late. We didn't find comparable estimates, so you should take the European one like as a lower estimate, but I mean it's 1 billion euros, so it's still a lot of money, and it's going to get worse because this is intuitive. The demand for flights has been increasing steadily. Well, it had a brief decrease in 9/11, of course, but has been increasing steadily. It's projected to be 70 million flights in 2020, and the last estimate I saw was like for the 2010, and I think there were 5 million less or something. So it is increasing. And this is a market when you cannot just expand. You cannot build more airports, more runways, and it's very difficult for airlines to establish more routes. So efficiency is the key. And this is why this is a problem that many people want to look into. But of course, here I talk to you about money, but we'd like to say that the problem is interesting in itself. Now, as Pablo already showed you, this kind of systems have rich dynamics, so that is already something interesting. We know that this kind of approach that we will describe now does give us good results for the US, so trying the same thing in Europe is kind of natural. And also I must say, well, this is entirely subjective, but I have seen a lot of interest in our perspective among the community of researchers in air transportation management. Here you see some conferences where and all of these are the track in complexity. So there is an interest in our point of view, and if you kindly give me 1 minute to feel good about myself, this is the last conference where we were, and in the complexity track, 2 out of 4 talks were by people from IFISC, and also Jose was in the committee, so but jokes aside, I mean, this should hopefully mean that we are not doing something that is completely wrong. This means that we are getting at least something right. That said, we want to describe the problem slightly more in detail, and of course we must begin with a definition. What do we mean by reactionary delay? Now, we say that a delay is reactionary if it's transferred from one flight to another. So my aircraft is late only because it has to wait for another aircraft. This can happen usually because the two flights share some resources. So they might be operated by the same aircraft, in which case it's obvious. There might be passengers that need to transfer between one flight and the other, and at least in some circumstances you have to wait for them. And there are crew members that might need to be transferred from one aircraft to the other. Also, there is another way to transfer delay between one flight and the other, and this is actually an important point because this is one of the big differences between how the US system works and how the European system works. There are physical limitations. You cannot have infinite aircrafts on the runway or in the same airspace. So this kind of limitations might mean someone has to be delayed. So you can also have a mechanism for transferring delays that works in this way, and we will see that in detail later. Here you can see that these are all the delays divided by cause for 2013, and you see that the reactionary delays are almost half of the total delay, so it's a big problem. What do we want to do about that? The idea is that we want to build agent-based models in which we simulate how the operations during one day take place, and we try to find out where do these reactionary delays begin, where do they go, and what is their impact, and what can be done to minimize this impact. Now, the idea is that as an input to our simulation, we use the schedules, so what the aircraft are supposed to do, and as an initial condition, the primary delays. And we see which kind of reactionary delays are generated. So the output of one simulation is a list of the flights as, according to the model, they actually happened in reality. That is the thing that we have to compare with the empirical data. And we have several parameters. I will talk about them later. In the model, the idea is that we want to find the set of parameters that give a best fit for a large set of days. Okay? The way we are doing that is that we look at the cluster of congested airports. Here, by congested, I mean with high average delay above a given threshold that it's relatively arbitrary, but we are using the average for the whole here. The size, the largest size that this cluster reaches throughout the day is the thing that we use to fit the parameters. And of course, if the model works, also other metrics that we can perform will be in agreement with what happens in reality. Now, there is something I have to describe now. Of course, you can imagine that in some cases, everything goes according to plan. There is a schedule, there are no big disruptions, everyone is on time, you don't have a big cluster of congested airports, you don't have high average delay. But when there are problems, when we see the delays, this can arise for two different reasons. One is that the schedules are inefficient. So even some relatively small primary delay can disrupt them. The other reason is that you might have external perturbation. Here I have listed some possibilities. By the way, I said riots, this is not a joke, this is something that actually happens and you can see it in the data. So we need a way to say what's going on, because in all of these cases, the system is going to react in a different way. So we expect that a model of normal operations will break down in these cases. For example, in case of a strike, you know generally in advance, at least 24 hours, that there is going to be a strike. The airport can react preemptively, and this is something, for example, that our models cannot consider. So it's useless if we try to model this kind of thing. Actually, it's something that we're planning to do in the future, and we are looking into it. But just to give you, how do we understand this thing? Well, Google is our friend in this case. So this is the year 2013. We have taken the worst 25% of days. This is a little cluttered, but I will explain you now. So for each one of the 25% worst days, we looked on Google News and we tried to find if we could give a cause to these problems. Now you see that here, here, and here you have these big clusters of days with high average delay, and these were weather problems. I mean, you look at the news and you read lots of flights cancelled because there were weather problems. This incredibly huge spike in here was a strike of the French. And this is also interesting because it did a complete mess. And here in green, these are the days where we were not able to find any cause for the delay. So we don't know for sure that there was no external cause, but these are the good candidates. Of course, you also have, if you have the data for those days, you also can, once you have a suspicion that there might be something going on, you also can look at the data and get confirmation. This is something that happened about 1 month ago. There was a huge fire in the airport at Rome, and you do see it in the data. So this is the day of the accident, and you see that the number of movements, departure and arrivals, dropped by 50% and more. So this is more or less the approach. Now I will describe what actually the model does. So, like I said, we have these 4 possible mechanisms for propagating delay. So, aircraft rotations, connections by crews or passengers, and air traffic flow management, which we will come to in a minute. Now, this is the first one. All of them, I mean, we are simulating all of them. This is the first one. So the idea is quite easy. You have an aircraft that arrives at the airport, and then turnaround time, that is the time needed to unload the passengers, bring in passengers from that have to take the next flight, refuel, and so on. This is something that you get directly from the data. It's the time between one flight and the other done by the same aircraft. But if the aircraft is late, so it arrives late, well, you can use this, you can reduce this buffer time to absorb the delay, but there is a minimum amount. This, I think, that is something established by law, by the way. There is a minimum amount under which you cannot go. Of course, it will be physically impossible. In the model, we are using the same minimum turnaround for all the aircraft. This is something that probably will be changed in the future, and we'll separate the turnaround times by model of aircraft. So, if you are too late, clearly the next flight in the rotation cannot depart because you are not physically there. And so, in this way, you have propagation from one flight to the next one. Slightly more complicated is the problem of the passenger connections. This is actually one of the big differences between what Pablo has been doing and what I'm doing, in the sense that this is something new. But it's something that can and will be also transferred to the US system. So we need to know what the passengers are doing. To do this, we have some market sector data that we bought from Sable, which is a company based on the US, which provides services to the airlines. So unfortunately, this means that the information about passengers that we have is absolutely private. We cannot share it. So maybe someone of you has a problem with that, but it's the only way we can know what's going on. This is basically data from purchase tickets. So if you want to go from here to Munich and you buy a ticket that has a connection through, I don't know, Rome, in their database, it will show that there is one guy that bought a ticket from here to Munich through Rome. So in this case, we have the passengers on the aircraft, they have to decide how to connect to next flights in the same airport, and we have a probability of connection that depends on the following things. So where the passenger is coming from, where he does the connection, and where does he want to go. And also it depends on the airlines which are operating the two flights, and not plural airlines, because in this case, this is a difference from what Pablo was doing. In this case, we allow connections between different airlines, as long as they are in the same alliance, because that is actually what happens in reality. Once we have these probabilities, we don't use them raw as they are, but we actually put them into this machinery. So we have an effective parameter alpha that allows us to tweak the probabilities of connection that we have in the model with respect to what we have in the data. So in here, WE is the probability to go to some flight. We have this parameter, so if it's negative, we are decreasing the probabilities of connecting and increasing the probability of staying where you are. You don't take a connection, so there is no propagation of delay, at least because of it. If we increase alpha, we have more connections that we see in the data. And well, of course, in the two extremes, we have that nobody connects on that for that particular route. Nobody connects for any route, and with alpha equals to 1, everybody is connecting. This is a parameter that is global, system-wide, so the probabilities, of course, change, but they are all scaled to the same parameter. Finally, we also have the crew connections. So the pilot of the aircraft may need to go to be transferred to another aircraft. Actually, there was a question in the why do they do that? The reason is that the most optimized schedule for an aircraft is not always the most optimized schedule for a person. In here, since there is absolutely no way you can get data for this, in here we are basically replicating what has been done in the US. So in each airport, we have a fraction of connecting passengers. So these are passengers and not crew members, but our idea is that the connections within the same airline usually happen in the operational basis of the airline. So if the fraction of connecting passenger is really high, that must mean we are dealing with a hub, and so it's a place where the crew connections can take place. And of course, this is also scaled by an effective parameter gamma. So, well, the impact of this whole thing is actually rather small, because we are already connecting the flights through the passengers, but people in the industry really like this kind of thing, so we put it. And then we arrive to one big difference between the US and Europe. Air traffic flow management. What does this mean? All the airports, and also actually the airspaces, but we are not considering them, all the airports, like I told you before, cannot support an infinite number of movements per hour. At some point, it's too crowded, and it's dangerous, of course. This is usually taken care of in the schedules. They don't allow a million aircraft to depart at the same time, but suppose that your capacity is 10 and you have 8 scheduled flights. 3 from the previous hour are delayed, so now you have 11 in your hour. You're going above capacity, and you cannot allow that. To deal with this, we implemented this mechanism. Now, this, of course, is a model, so this is an oversimplification of what happens in reality. What happens in reality is similar to that, but it's extremely complex. So you have to trust me that this is actually a decent representation of what's going on. 1 hour with a given capacity, so we divide this hour in a number of slots according to the capacity. And we have several flights, one to depart or arrive in the airport in that time, during that hour. So they get, each one of them gets to pick one of the slots, one of these time intervals, and the priority in which they take a slot is on a first planned, first served basis. This is a huge difference with respect to the US, because in that case, what we had was just that. In this same situation, the aircrafts are put in a queue. And then you process the first one of the queue as time goes on. In this case, we have this more complicated mechanism, and well, this is not actually all that there is to it, because of course you have the conflicting regulations. So one airport is crowded and wants you to depart at a certain time, but the arrival airport is also crowded and it wants you to depart at a different time. In this case, well, we do the simplest thing, so that the conflict is solved by choosing the worst regulation. So the later time, that hopefully is the best one for both arrival and departure, is chosen. Then we have to put some data in this model, right? And since I've given this title to this section of the talk, you might imagine that this is not completely straightforward. Well, in the US, if you want some data, you do this. You go to this website, you click download, that's here, and you're fine. It turns out that in Europe, things are a little bit more complicated. Now, our original plan was to receive data from the Central Office for Delay Analysis, which is a part of Eurocontrol, and they have some really, really good data. When they said we're going to give you the data, we were extremely happy, but they only gave us 1 day. Now, this is not completely useless, because we are able to reproduce what we got in that day, but clearly it is not enough. I told you that we want many days, not just one. So we need an alternative data source. And I will show what this later. First, this is what we get. This is the size of the cluster of congested airports. So this is, I don't remember if Pablo showed exactly the same plots, but this is comparable to what we have in the US. So I have highlighted what you get if you only put the primary delays into the system. I mean, it's not a coincidence. I mean, we are recreating delay that it's not put as input. There is something that is happening. So when we saw this and there were going to be more days, we were really, really happy. Anyway, this paper is just to show you that this is actually a problem that not only we have. Actually, we are the only one. We are the only one who managed to get this data. I mean, they never gave anything to anybody. It's not that they don't want, it's because legal trouble, of course. So as you can see here, someone actually wrote a paper on this problem, so it's not only us. And well, this allows me to make an interesting point, I think, because during Pablo's talk, I think it was Hingo, who asked, yes, but what can you actually do with this kind of models? And my hope is that if we show that you can get something interesting out of these models, maybe the access to the data will be easier. I mean, all this thing is, like I said, completely available for the US, so it's only a problem of wanting to do that. Anyway, here is our data source. Now, I don't know if you are familiar with this website, but there is time, so maybe I can show it to you. Okay. Something will happen, hopefully. Okay, so this is a website where you can go and look at whatever is happening in the skies. Of course, you might want to know, okay, you have this data, but is it any good? I mean, there is a reason. If it was so good, everybody would be using that. Well, as far as we know, it's actually quite good, this data. The coverage is quite high. What we get is between 14,000 and 17,000 flights per day. And that is comparable with what we could get from the official source. Also, in this case, there is also an advantage. Let me show you. If you click on you get all the information that you want, and more importantly, you get the airline. In that data I showed you before, we did not have the name of the airline, and we had to reconstruct it ourselves because they didn't want us to know. But I mean, I know that I am picturing this like a meaningless thing, but actually it does have meaning. Now, remember, for example, that in one of the first slides, I showed you a pie chart with the delay by cause. That is an awful amount of detail. If you have detailed data on what the airlines are doing, then you can write a paper saying this airline is doing a terrible job. And they clearly don't want that. In fact, if you remember, Pablo also had a plot by airline, and in that case, the name of the airlines were obfuscated. So you have to tread carefully when doing these things.
That's why they're perfectly free to say you are. I mean, what's the problem? If you use public data, you can analyze that, and you can say that the airline is correct. Sorry?
They don't want it to be public.
Yeah, that is.
Exactly.
No, but this is.
No, I mean.
So they know.
But you know how
This code.
this is.
No, I mean, no.
Official
He's right in the sense that we were able to, at least for the 40 biggest airlines in Europe, we were able to identify them. So you can do that, but still they don't want to make it easy.
No, but this, I mean, the point is, this is not, this data,
What
is public is the broadcast signal each plane is sending all the time.
Yes.
And this is people put receivers at home
Yes.
to pick the signal.
I mean, you cannot.
It's not an official organization compiling this. It's public. These people compiling data and putting it on the web.
So how does it work?
Well, he just said so. It's people putting receivers, voluntary.
So is somebody paid put receivers to?
I mean, you pay.
I don't know.
I mean, it's like an. I know it's weird, but it's like an hobbyist thing. So you buy this receiver, the price is.
The thing is free, Bruno. They can send the receiver at home for free, and also you have 1 year of premium subscription to the site.
I have no idea about this, but good to know.
You can get for free. You can put on your roof. Just connect.
By the way, the problem with this is actually that you have to be slightly more clever when you collect the data, because since it's a voluntary thing, the coverage geographically is not going to be uniform. So in fact, the first thing that we were doing was to take a snapshot of the system at fixed intervals of time. And it was a mess because you might have an aircraft that enters a region receiver and it disappears. Then it suddenly reappears somewhere else. So, but what you can actually do is another thing, because you can, now I have selected a flight and it's showing me the flight, but I can click.
So how do they win money out of this? Who pays for this? I mean, you are
Well, I mean, I'm seeing some ads.
Subscriptions, we have with also the app for the iPhone or Android. It's not free.
You pay for
yes,
the app?
For the app and also for the premium subscription on the website to see everything without limits.
And who is interested in that?
Me, for instance.
That for the
The app is awesome. It's fantastic.
I have it for free.
Just-
I have it for free.
Okay, but I mean, if you look at the airport and not at the flights, you can get a list of what is happening. So you don't have strange things, and I mean, when we actually analyze this data, the amount of strange things that we find is quite low. Probably I should tell you, I mean, in some cases you find holes in rotations. So you have you group the aircrafts by the flights by aircraft. You have all your rotations, and sometimes you find holes, which means that your aircraft arrives in Palma, but then it departs from Barcelona. Now, in this case, we try to do the most obvious thing, which is inserting another flight in the rotation that goes from Parma to Barcelona. We need to do a very small amount of this stuff to actually fix everything, which is good. And this is, I'm not sure if I am allowed to say this, but this is a problem that also was in the official data. So, I mean, this might not be perfect, but if you compare it with the official sources, as far as we can see, it is good. The coverage is good. The scheduled departures are correct, all of them. So this leaves us only with a problem, which is which delays are primary and which ones are reactionary. Because in the CODA data, they were clearly labeled. I mean, they have their database that is actually built from the flight plans. So the things that the pilots send to the control towers. And so they know exactly everything that's happening. In flight radar data, we don't have information if the delay is primary or not. Now, in the US, what you can do is that you can take only the first delay of the rotation and say, okay, this is primary, the other ones are reactionary, and it works. If you try to replicate the same thing with this data, it doesn't. So actually this is what we are working on now, understanding which delays are primary and which are reactionary. But something that I can tell you right now is the difference. And this is probably one of the biggest differences between the two systems. Now, to explain this, first, show this picture. This was made by Pablo, and it's for the US. This is the evolution of the cluster in 4 different cases. Here, we only have the plane rotations, so the other mechanisms for propagating delays are deactivated. You can in this case, you can only propagate delay. If the aircraft is late, it will propagate delay to its own next flight. And you see that you don't recreate the congestion. Nothing happens, and it's wrong because it happens in reality. With all the mechanisms activated, you get this. And with only the passenger connections activated, you get this, which is basically the same. So for the US, what we can say is that the connections are by far the dominating mechanism in propagating delay. In Europe, this is not the case. Well, I mean, the idea is that since you are propagating a lot of delay through the connections, you don't need to get the primary delays right. Because the first flights in the rotation, of course you have to put the delay in them because they're not receiving delay from anything else. They're the first ones of the day. But for the successive ones, well, they are going to get delay anyway because of the connections. So even if you don't put the correct primary delay in there, they are still, I mean, the idea is that I'm waiting for a passenger that is my own passenger. So I'm 10 minutes late. But then I have to wait half an hour for a passenger that comes to another flight. The first passenger is invisible. So in this case, this is the dominant mechanism. In Europe, this does not happen a lot. Now, the first reason is that we have the so-called point-to-point airlines. This will be the low-cost airlines, but people in the industry tend to be upset when we use this term, so point-to-point. So Ryanair, EasyJet, and the likes. They don't do any passenger connections. You cannot go to the website of Ryanair and build a flight ticket that has two legs. If I want to go from here to Madrid and from Madrid to Rome with Ryanair, I have to buy two separate tickets. And if the first flight is late or cancelled, my own problem. It happens that these airlines make up for like 20% of the total traffic in Europe. If you look at it day by day, you will find like Ryanair 1,000, 1,500 flights. So this is one factor. Now, like I said, this is a work in progress, so I'm not showing anything yet about this, but we do have some ideas about how to fix that. So one is to look at which airports are generators or absorbers of delays. I mean, if you go and look at the airports, you will find that for some of them, the inbound delay is higher than the outbound delay. So flights arrive and usually can recover their delay. Otherwise, you can have the opposite. Airports where you arrive with low delay and you go out with high delay. We can assume that if the airport is an absorber of delay, it means that it's not a hub, connections do not take place in there, and maybe you can take that delay as primary. And also another thing, this is actually the very thing that I'm doing, you can try to match the schedule with the passenger connectivity data precisely. So you can say, I have the schedule, I have this flight, I can look backwards in time, and I can find if there is someone who can propagate delay to this flight. If there is no one, then the delay is primary. But this is, I mean, is also something that showed here. I mean, this is the cumulative total delay during the day. And you can see that the primary delay, okay, it's much smaller than the total one, but it's big. And there is no way you can get something like that in the US. So I mean, this is another difference. And split second, I am done. So, if you have any questions, suggestions, throw vegetables at me, whatever.
So thank you very much for the nice presentation. I'm sure there's questions or comments. Yes, please.
I have a question about the different regulations between the US and Europe. In the model, in US, you said that we are putting the aircraft in PQ.
Yes.
And why in Europe is so different the mechanisms?
Because it's Europe.
Okay.
I mean, we do really like, I mean, this is I'm kind of sad that that part got only into a slide because it's something that I mean, actually, about 40% of the total work went into that part. That is an extremely complicated system, and hopefully no one is watching, but my feeling is that very, very few people know how it works. We had to change that mechanism like 3 times, and actually some comments from referees were life-saving for that. But it is a complicated mechanism, and there are many things also that we are not taking into account, because we are not taking into account the airspace. I mean, in theory, you can have a regulation in your departure airport, one in your arrival, and one in the middle, or 2, one for each different airspace. The way they do it, it's actually automated. They do some kind of algorithm that does that. We do know how it works. We have to use a simplified version because there is no way you can reconstruct from the data how the thing works.
So may I ask in this context how you explicitly put that in the model? Because in the end you have a state of your airport, which is the congestion. And then you have a reaction debate, which is a function of this level of congestion at these airports. So do you use an explicit?
No, sorry.
Function, or do you have a statistical relationship?
My bad. Actually, the congestion, I meant 2 different things in the sense that when I say, well, it's slightly incorrect to say congestion to refer to an airport with high delay. What I mean actually is that congestion means that too many flights want to depart from there or to arrive in there. So the idea is that at the beginning of each hour, we check all the airports and we check every flight that wants to go there. If they are too many, we say, okay, we have to do a regulation. So the airport gives to the flights, the airlines, if you want, these possibilities, and they get to choose one. And that's it. But no, it's not a function of the delay. Also, I mean, the priority is given on a first plan, first served basis. So if you have a lot of delay, but you were supposed to depart very early, you are going to get an early slot. This is one of the points where there is an oversimplification, because actually the priority is given to the one that gives first plan. But this is something we cannot simulate because there is no way, at least as far as I know, to know when the pilot did send to the control tower the plan. So we are using the scheduled departure for that.
So you cannot distinguish, for example, whether the US system or the European system is working in the end better?
This is something that one of the very next things to go, in the sense that, well, Paolo now is not here, but when we presented those 2 papers at the conference, they proposed us to merge them in one that is going to be published on an ATM journal, and in that one, which we will do in the next month, we will do exactly this thing. So we'll try to run an European schedule with the US system and with the European system and the opposite is. But I mean, this is a point that I have skipped over because I didn't want to get too much into the boring details. But since you asked, here there is also the thing that the capacities have to be taken from somewhere. In the sense that you have to do this regulation, you need to know how many flights you can have.
I understand that there is can be delays for the rotation of the queue, but I've never been aware that some plane has waited for me.
No, they don't. That is why we used an effective parameter.
So,
I mean,
so are really planes waiting for someone from
yes.
VIPs or for?
Well, probably. I mean, probably not for you and me. At least as long as we travel in business class. By the way, this is also something we are thinking about in the sense that now we are downloading data that is separated by ticket class. So obviously they don't wait indefinitely, but probably if they have to wait 10 minutes or 20 for a first class passenger, maybe it's better to wait. But I mean, I assure you that in some, not for us, but in some cases they wait.
I think it doesn't matter the class that you are traveling, because I've been waiting for a flight. They only don't want me or a passenger to stay in the airport because it will cost more money. Because then I have to be sent if my ticket is a connection and I lost my flight for 5 minutes. Better to wait 5 minutes for this passenger. It doesn't matter.
Yeah, well, I mean, it's
because after that, I'm going to cost much more money to the airline. Because, for example, once I was traveling to Rome, and they had to make a trip through Frankfurt from Lisbon instead of going directly. And this is because I lost my flight. So I don't think it's something that related to the class, and they do wait.
no, I mean,
if they cannot solve the delay.
Well, I don't know. I don't know what is the percentage. From my experience, the percentage is 0. So I think the waiting proportion of waiting events should be small, at least in Europe.
Yes.
no, but I mean, I mentioned the class because it's more expensive. I mean, if you are in first class, they send you somewhere else, they have to give you a first class ticket. So I mean, in the case of first class, they are more eager to do that because it's more money. But I mean, I've heard one guy that was CEO of, I don't remember which company, saying that they had organized a dinner at the beach for some passengers that were left in the airport. So, I mean, they also can get creative with this kind of thing.
I think it's probably often even a lot more practical. If luggage is checked through and you have the luggage on the plane, you'd rather wait for the
Yes, also, I mean, there is some
delays even worse.
image damage that you can get. I mean, airlines care about passenger satisfaction, so as long as they cannot blame if they can blame someone else, they don't care. But if the problem is on them, it's in their interest to solve it.
The problem is never on them.
No, you're right. You're right. In fact, if you listen,
The of the wait arrival of the plane.
but later arrival of the plane might depend on them.
Yes, that's what you think. That's what you think.
But
That's what I think. Not it.
well, I mean, if it's later arrival of the plane, it means that it's reactionary.
Yeah.
So you'd have to.
That's-
They are in the system they use. Those are not classified as blame the airline.
More questions? Maybe one more from my side. What you're doing is already a very involved and complicated model. with quite involved data. So just a question from a fundamental point of view. If you want to learn, for example, about how really delays propagate in a network, isn't the model already too complicated? Do you have plans also to go to simplified models in order to understand the mechanisms that
This is actually, I really like that you're asking this question, because this is a very important point. But you see, this is what most certainly I think would need to be done. But for this kind of field, probably, this is mostly an engineering field. So when we go to conferences, basically I'm the only physicist there. So we are kind of in the two extremes. So if you look at the kind of models that get presented in these kind of conferences, they are all extremely complicated. This actually makes sense because it's where the money comes from. So who gives you this? I don't care about fundamental stuff. I want just that you solve me this problem right now. Personally, I think it's a problem. But it's a problem for that reason. If you want to do the things in a lot of detail, you need very detailed data. Having very detailed data is hard. And in fact, this thing we are trying to do with the flight radar data, to my knowledge, nobody has done that. You can find studies similar to this, but with only a few days and no plan to get anything more. You can get something very detailed, but only at the level of the airport. But if you do something large scale, you have to cut something. And this is a problem for the validation, of course. Because you validated, yes, but only with this. I agree with you. It would be interesting also, besides adding stuff, also to remove stuff. To see but that is what we do when the project is over. Okay. It's over in September, so unless we get an extension.
Sure, it's always the question who gives the money.
Yes.
All right, so let's thank Bruno once again.